Algebra 2 students, this week we're going to learn about exponential functions, exponential growth and decay. So very relevant when we are in the time of a pandemic. So before we get started, I hope you had a really good almost week off. I hope you were able to relax, have some fun, and just feel refreshed going into second semester. Okay? All right, well, let's just go ahead and get started here. An exponential function is one where we have a base, b, that is some number. It sometimes can have a multiplier in front, an a, as you see in our formula here. But then always has our exponent as x, our independent variable. Okay. The one rule with b, our base, is it cannot equal 1. Because 1 to any power is just itself, we'd end up with a flat line. Our exponential parent function is right here. It's 2 to the power of x. That function is also what you see here in the table and what you see in the graph. So let's take a closer look at that. We can see that our y-intercept of our graph is 1. We can also see that in the table. So that's a little bit different from our other parent functions. A lot of them went through 0, 0. This one does not. And then what happens is we see it doubling after that. So 1 times 2 is 2, 2 times 2 is 4, 4 times 2 is 8, and so on. And so that's where we get that exponential growth. Notice when we go the other direction, we're not multiplying by 2. We're dividing it by 2. We're making halves. So half, a fourth. If I keep going with that, I would get an eighth, a 16th, a 32nd. Would I ever actually hit 0 if I keep taking half, a 64th, 128th? No, I'll never actually hit 0. And so that's why what you'll see on this graph here is you'll see it approaching the x-axis, approaching 0, but never actually crossing it. We have a special name for that, and what that's called is an asymptote. It's a line that the graphed function will approach, but it will never actually cross. This is our first function we'll learn about with an asymptote. It is not the last. Okay, 2 more things of note with our exponential functions is that when b is greater than 0, we have what we call exponential growth. So in our parent function, the b value, the base of the exponent is 2. That's greater than 1, so we have exponential growth. Now, when the base of the exponent is a fraction or a decimal, it's something that's between 0 and 1, we call that exponential decay. And the graph will go downhill. It'll decrease as x increases. So we're going to look at a couple functions, and we are going to determine first if we're seeing exponential growth or decay. So we'll look at the base of the exponent, and then we'll look at the graph. So here's our first one, 10 times 3/4 to the power of x. The base of the exponent is the 3/4. 10 is a multiplier. It's a stretch. 3/4 is the actual base. 3/4 is greater than 0, but it's also less than 1. So we would call this exponential decay. Now to graph this, we can make a table. It is also okay to use Desmos. So I'm going to pull up a Desmos graph right behind me here. And here we can see this graph on Desmos. I can see my y-intercept is 10. If I look over to the right, I notice that it is approaching the x-axis again. The asymptote is 0, y equals 0, or the x-axis. So if I zoom out, it'll never actually go below that x-axis. Now, in order to graph this properly, I want to make sure I include a couple key points. So I'm going to pull my notes back up. Hopefully they'll cooperate and come up here. There they are. So when I graph this, I want to be intentional about showing the y-intercept, which was 10, and I want to show the asymptote clearly. So I'm going to show it like approaching the x-axis, but not actually crossing it. Let's look at something we maybe notice. The y-intercept is 10. That's an important thing. Where do you see 10 in the function? You're right, it's right there. It's the multiplier. So let's look at our next one. What's the multiplier in this next function? It's 100. So what's your prediction for your y-intercept? 100, that's my prediction too. Before we go ahead and type that in though, let's label this. I've got 1.05 is my exponent, my base. That is greater than 1. That means that this is exponential growth. Let's head over to Desmos and make a graph. So I have y equals 100, times 1.05 to the power of x. So remember, our prediction is the y-intercept is 100. I don't see 100 on my graph, so that's why I don't see it yet. Here it is. Our prediction's correct. The y-intercept's 100. This is exponential growth, so I see it skyrocketing upward. And if I zoom out some more and pull it to the side, I'll see that, again, my asymptote is the x-axis. Now, in order for that asymptote to shift above or below the x-axis, we would expect to see a shift in our function, right? So we would expect to see a plus or a minus at the end here. That's how you'll know that your asymptote is something other than 0. All right, let's make a nice sketch of this graph, and then we'll look at one application. Okay, so sketch, y-intercept is 100, and it's going to go up from there. Not my best sketch, but you get the idea. All right, so the main application we're going to look at, and the one we'll look at first for our exponential functions, is looking at percent increase and decrease. And we can model that with this formula. So we have our final amount here is on the left. And then we have an initial amount that we'll put in as our multiplier. The rate of increase or decrease goes in the parentheses. And notice it has the 1 plus or minus. So if you have a rate increase of 5%, you would add 0.05 because it's an increase, so you add, and a percent you change to a decimal. If it is a decrease of 5%, we would subtract. We subtract for the decreases, add for the increases. And then t is the number of time periods. So we're going to use this formula to solve a couple of problems. So it says Clara invests $5,000 in an account. Well, if she's investing it, that's her initial amount, that's the A. And it pays 6.25% interest per year. If it's paying interest, it's increasing interest. I'm going to do the 1 plus that rate. After how many years will her investment be worth $10,000? That's a final amount. So let's go ahead and put those in. So our final amount is $10,000 equals our initial amount, which is $5,000. And then we'll do 1 plus 6.25%. That would be 0.0625 to the t. Now we don't have the skills yet to solve for that t, okay? So what we're going to do is use a graph to help us solve. I have two things here. I have a value of 10,000, so that's going to be my y1, and then I have this other side, my initial amount and my interest rate. That's going to be my y2. And where those two things intersect, that will be the number of time periods. So let's use Desmos to help us. So we have one of our y values is just equal to 10,000. Okay. The next one, we have y equals our initial amount, 5,000, times 1.0625 to the power of t. We'll use x in Desmos. So we can see this exponential growth function. We know our y-intercept is 5,000, so we need to do a bunch of zooming out. But we also know we're looking for this intersection point at 10,000. So I think what I'm going to do, I'll move my head over. I'm going to go to Tools here, and I'm going to set my window. So I know my y-axis, I want it to go up to 10,000, but maybe a little bit more, so 10,100. X-axis, we're probably not going to be talking 500 years. I'm going to have it go up to 50. Oops, that's what it's counting by. Leave that. So I want the y can go from 0 up to 10,100. X-axis can go from 0, because we're talking about time, up to, let's say, 50. All right, now my graph is a little bit more readable. Here's my y-intercept at 5,000, and here's where they intersect. So we'll see that dollar amount of $10,000, they intersect at 11.433. So 11.433 is where they intersect. But the question is, after how many years will the investment be worth $10,000? Well, at 11 years, it's not quite that much, so we're going to need to round this up. So it'll say after 12 years. Assume that you need a whole number answer for that, unless stated otherwise. All right, one more, and then we'll wrap this up. I know this video is getting long, but it's the only one. All right, a city population was initially 15,500, starting amount. It's been dropping by 3% a year. Subtract 3%. Write an exponential function and graph the function. Use the graph to predict when the population will drop below 8,000. So our exponential function will be y equals our starting value, 15,500. I'm going to have to subtract 3%, so I'm going to take 1 minus 0.03 to get 0.97 to the power of x. And I want to know when it's going to drop below 8,000. So what I'm going to be looking for is, where does it cross 8,000? Okay, and then just after that, it'll drop below it. Let's head back to Desmos one more time. All right, move my head again. We'll go down here for fun. All right, y equals 8,000, and then y equals 15,500 times 0.97 to the power of x. Our window works. Okay, we can't see our y-intercept, but that's okay. We can see this intersection point. We know we have exponential decay because our base is less than 1, and we can see it heading downhill and crossing that 8,000 mark at 21.714 years. So how many years will it dip below 8,000? Well, if we simply just round to 22, 22 years would be our answer. So let's go ahead and write that down. 22 years. Okay. All right, so that's it for this week. Okay, identifying growth and decay, graphing, and then writing it in that percent increase and decrease. I suggest that you take a few minutes with your notes and you fill in this chart, okay, to show what you know about growth and decay. So the value of B for growth is greater than 1, and for decay, that value of B is greater than 0, but less than 1, okay? So that's how we would fill this out. So I suggest you take a few minutes and organize your thoughts there. All right. Have a good week, everybody.